Ladies and gentlemen, thank you for coming. For more than 40 years, I have been a scientist. And I've been looking at the past, that is geology. And what interests me is putting geology, archaeology and history together to understand our place on this planet. Now, science is married to evidence. It doesn't matter if you speak Czech, Spanish or Urdu. Science is married to evidence. And that evidence is collected by observation, by measurement and by experiment. And you never believe the measurements. You do them again, and you do them again, and you do them again. And eventually you have enough evidence that you need to explain. And this evidence you explain with a scientific theory. If you get new evidence that is validated, you make your theory better. You refine your theory. Science doesn't care whether you like the theory or not. Science has no politics. Science doesn't care whether you're black or white or yellow. It's all about evidence. And the evidence that I see from the past is remarkable. I give you a very short history. There was a Thursday, 4,567 million years ago, when this planet formed. And for the first 800 million years, we got bombarded by asteroids. They might have brought in water. They certainly brought in amino acids. And there was one day, about 4,000 million years ago, when something amazing happened. It rained. And it rained on planet Earth for the first time. And as soon as we had rain, we saw life. Yes, it was primitive life. It was bacterial life. And most of life on Earth is bacteria. 90% of your cells are bacteria. 15% of your weight is bacteria. You have 5,500 bacteria in your body. Bacteria rule the world. It's not trees, it's not whales, it's not humans, it's bacteria. And for 80% of time, this planet has been hotter than now. It's been wetter than now. And the key to climate on planet Earth are the ice ages. And we have had 6 great ice ages. The first ice age tells us a wonderful story. That ice age took place 2,500 million years ago. And the ice sheets were expanding and contracting. That's what ice does, expands and contracts. That ice age had ice at sea level. That ice age had ice at the equator. And the scientific question is, how did this happen? How did we suddenly have an ice age and then the ice age suddenly stopped? And there's a simple answer. We don't know. And that's marvellous. That's what science is about. It's a detective story. But what we do know is when the ice sheets finally retreated, all of the finely ground up minerals and rocks were washed into the oceans. We added fertiliser to the oceans. And all of a sudden, life in the oceans, which was bacteria, said, I'll have some of this. This is beautiful. And bacteria diverged into one type of bacteria that has a cell wall and a nucleus, and another type of bacteria which has no nucleus. And one type of bacteria started to pump out a very poisonous gas. And the atmosphere started to get a little bit of this poisonous gas in it. That gas is oxygen. One group of bacteria started to die because of oxidation. You still have some of that bacteria in your stomach. We still find it in bogs and swamps. But we had genocide. We had oxygen entering the atmosphere. It dissolved in the oceans. It dissolved in water. We changed from soils that were green in colour to red in colour. We precipitated iron oxide from the oceans to form the big iron ore deposits of Brazil and Australia and Canada. And so what we see is a remarkable link between climate, the diversity of life, the atmosphere, the oceans and rocks. So if you want to understand climate, you have to understand all of that. You just can't look at the atmosphere. After that ice age, we went back into our normal warm times. And 800 million years ago, the same thing happened again. We had another huge ice age, again at sea level, again at the equator. We had 40 kilometres of ice at the equator. How did that happen? We don't know. Why did the ice go away? We don't know. Sea level changed by 1.5 kilometres up and down as the ice sheets expanded and contracted. But when that ice age finished, all of the nutrients were washed into the oceans. By then the atmosphere had a little bit more oxygen in it. And in the oceans, the bacteria again diversified and we got multicellular life. So again, we see the same thing, a relationship between climate, life. And at that period of time, we had the rock, dolomite, that was precipitating all over the planet. And we can make dolomite in the laboratory. And you can only make dolomite when you have more than 20% carbon dioxide in the atmosphere. So here we had an ice age when we had a very high carbon dioxide content. Clearly, the carbon dioxide had not heated the planet. And then we came to a marvellous period of time when we had this multicellular life appear, and then there was an explosion of life. A new life used carbon dioxide for shells. New life started to grow coral reefs. And this new life exploded into 100 major phyla of life. We've never seen a new phylum of life since then. Suddenly we got this explosion of life. The atmosphere had a high carbon dioxide content. The oxygen content was still getting higher. And that's absolutely marvellous. We can see the natural sequestration of carbon dioxide into life. And then the inevitable process occurred. We had a mass extinction of life. Mass extinctions are quite normal. This was a mass extinction of complex life. We don't really know why we got that mass extinction. And at about that time, we started to see life appear on land. We started to see vegetation. For 10% of time, we've had plants on the land. The rest of the time, we've had no plants. So we then came back into a cool period, another small ice age. Then we warmed up again, and then we had another great mass extinction 360 million years ago. And we have large meteorite impact craters in Sweden. We vaporised some of Sweden, which was probably a good thing. And we had massive volcanoes around the world. We had an extinction of complex life. About 80% of life became extinct. And we came back, bounced back, and we started to have an enormous growth of vegetation on the planet. The oxygen content of the atmosphere was almost double what it is now. We had massive forest fires with all the oxygen and the methane from the decomposition of forests. And we see in the geological record we've had a period of time where we've got insects with wingspans like this, where we've had forest fires, landslides, explosions of the atmosphere. And we sequestered that oxygen into the soils and into the rocks. We sequestered the high carbon dioxide in the atmosphere into the plants. And then we went back to being a normal planet. And then we had another ice age. This time it was at the pole. So where I live, we were at Antarctica, and where you live, you're about at where the Persian Gulf is. It was warm for you. There were tidal flats. There were red dune sands. And where I live in Australia, we had ice, and we had coal forming in these cold conditions. That ice age was probably because an ancient continent went over the pole, moved across the pole. And that ice age finished almost instantaneously at 251 million years ago, when we had 96% of all life on Earth became extinct, all complex life. Suddenly there was an extinction. We don't know what caused that extinction, but we think it was impacts and volcanoes in Siberia, and the volcanoes putting sulfur-rich gases into the atmosphere. That killed the plants. When it rained, we had acid rain. That killed life in the top of the ocean. And that mass extinction took about 10 million years for us to recover from. But we did. And we went back into the normal warm times. Another mass extinction from asteroid impacts 217 million years ago. And then back into warm times, and then suddenly another small ice age, which we see in some parts of the world. It wasn't global. And then we went back into warm times again. And so 100 million years ago, we had a warm Antarctica. We can see that we have tropical vegetation fossils in Antarctica. 100 million years ago, there were volcanoes there. 100 million years ago, there was a little bit of ice on top of the mountains in Antarctica. And 100 million years ago, we started to shape the world for the climate we enjoy today. Now, you've all heard about the next mass extinction. This was the mass extinction at 65 million years ago. This was a mass extinction where there was, as the story goes, there was an asteroid coming down. It was going to hit Texas. It missed, and it hit Mexico, vaporised bits of Mexico. Dinosaurs died. Wonderful story. Terrific story with an asteroid with dead dinosaur written on it. And it killed off the dinosaurs and everyone was happy. The problem is that might not be the case. We are now finding that that impact in Mexico was about 300,000 years before the dinosaurs became extinct. Something else made the dinosaurs extinct. And at that period of time, 300,000 years after the dinosaurs, after the impact in Mexico, we had huge volcanoes in India. These put out sulfur-rich gases into the atmosphere. We had acid rain, killed off the vegetation, so the dinosaurs had nothing to eat. Made the top of the oceans acid. That killed off life. So this is what science is about. We had this beautiful theory for killing the dinosaurs. It was wonderful. And it's probably not true. Why? Because we have new evidence. And science is married to evidence. So no theory is there forever. And there was a consensus that the dinosaurs were as a result of an asteroid impact. The problem is that 2,350 years ago, Socrates would have said, no, that's an illogical argument. You cannot argue from consensus. You cannot argue from authority. You argue from data. Unfortunately, many people still argue from consensus and have forgotten the logic that the Greeks gave us. 100 million years ago in Australia, we had a wonderful thing that happened to us. We started to move away from Antarctica, and we still are. We're moving north about that much every year. And so 100 million years ago, we got rid of New Zealand, and a good thing. And 100 million years ago, we got rid of India, and India started to move north. And 50 million years ago, India hit Asia and pushed up the Tibetan Plateau. That changed the jet stream. North of the Tibetan Plateau is desert. On the south, we have all the rocks reflecting the heat, and we drag up warm, moist air and give India the monsoon. Putting up mountains changes climate. We've seen it before, it's happening again. Every time you put up mountains, push up mountains, you form new soil. And to form new soil, you take carbon dioxide out of the atmosphere. So the planet is dynamic. But our current ice age starts from a process that occurred 37 million years ago. 37 million years ago, South America pulled away from Antarctica, and we set up the circumpolar current, which isolated Antarctica. Most of the world's surface heat is held in water. It is not held in the air. You can do the experiment at home. Run a hot bath, and the air in the bathroom gets warm. Run a cold bath and have a heater in the bathroom. The water doesn't warm up. The air does, but the water doesn't. Water has a very high heat capacity. And when we isolated Antarctica, it started to cool down. And 34 million years ago, we started the current ice age that we are in. And Antarctica ended up with ice. And that ice on Antarctica has been growing and disappearing and growing and retreating and expanding. We are in an ice age. It is rare to see ice on planet Earth. We are living in that period of time when ice sheets are growing and retreating. And about 20 million years ago, it suddenly warmed up a little bit. Then it cooled down again. And we kept cooling and cooling and cooling and cooling until about 6 million years ago. And 6 million years ago, the primates had a choice to make. Did they become extinct, or did they walk? And we know they walked from the hip structure and from footprints. And you, hominids, appeared because it got very cold and you had to move from what was a rainforest. It then retreated into little copses of trees. You had to move to live. If you didn't, you died. And 6 million years ago, we got so cold that other slight changes on the Earth started to affect temperature. Every 100,000 years, we go from a circular to elliptical orbit of the Earth. So we get closer to the sun for 10,000 years and a little bit far away from the sun for 90,000 years. And every 41,000 years, the axis of the Earth changes a little bit. So we get closer to the sun or further from the sun. And every 20,000 years or so, the Earth wobbles a little bit like a top. So we get closer to the sun or further from the sun. Once we'd cooled down enough, these slight changes in the orbit changed the shape, changed temperature. They changed the ice sheets. And we started to cool down with cycles of cold and warm and cold and warm. And about 2.5 million years ago, we suddenly got very cold because of the volcanoes in the Panama, and they joined North America to South America. So we couldn't move water between the Pacific and the Atlantic Oceans. We changed the heat balance. 2.5 million years ago, we had a supernoval eruption out there in space. And 2.5 million years ago, we got bombarded by cosmic particles. 2.5 million years ago, we had a lot more clouds because of the cosmic particles. And we got cooler because of the clouds. So two things happened coincidentally. Closing up the waterway between the Atlantic and the Pacific, and a lot more clouds. And you evolved. You evolved very quickly. You evolved into Homo, the genus Homo, and the species Habilis, handyman. You had enough brains to invent fire. And at that period of time, the hominids who were vegetarians, they became extinct. The hominids who ate meat, especially cooked meat, lived because you can metabolise protein much better when it's cooked. And the hominids we know could talk because of the neck structure and the Broca's area in the brain. They could communicate. They probably had about 300 words, probably had as many words in their language as your average footballer. But they could talk, and you need talk for hunting. And so you are here, you as Homo are here because of cooling. And then we kept going through cycles of cool and warm and cool and warm. And the last warm period, called the interglacial, was between 128,000 years ago and 116,000 years ago. And sea level then was 7 metres higher than now. It was at least 5 degrees warmer. We had 4 hominids living on planet Earth. You, Homo sapiens. We had the Neanderthals, Homo neanderthalensis. We had the hobbits. These are the small Homo floresiensis from Indonesia, and Homo erectus, upright humans. What we have in warm times is more food. What we have in warm times is speciation. Warm times are lovely, they're very good. And then it started to cool down. It started to cool down 116,000 years ago because of the change in the Earth's orbit from circular to elliptical. And we started to cool very quickly. The ice sheets got bigger. You humans were suffering, and you almost became extinct. 74,000 years ago, we had a supervolcano explode in Indonesia. We filled both hemispheres with aerosols because Indonesia is tropical. Now, a big volcano like Krakatoa or Santorini will blast out 30 cubic kilometres of aerosols. When Toba erupted, it blasted out 3,000 cubic kilometres of aerosols. We filled the atmosphere with aerosols. We lost the tropical vegetation. People moved north and south from the tropics. We very nearly became extinct. The geneticists tell us that we had a genetic blockage then. We probably went down to 8,000 Homo sapiens. We very nearly died. And we put pressure on many other organisms in the planet. And we kept cooling and cooling and cooling and cooling. And during that cooling, we lost the Homo floresiensis. They died. We lost the Neanderthals. They died. And we lost the Homo habilis. They died. But we survived because we could adapt. And we still adapt. We live on the ice. We live in the mountains. We live in the tropics. We live in the deserts. We have adapted to all sorts of different environments. And 20,000 years ago, we had much of the northern hemisphere covered with ice. Scandinavia had 5 kilometres of ice on it. So we put 5 kilometres of ice on Scandinavia and it sinks. That ice is now gone and Scandinavia is rising. We can measure it. So this then raises a very interesting question. When people talk about sea level, they're only giving you half the story. The land level goes up and down also. And we see that in history. The Roman port of Ephesus is 15 kilometres inland and 7 metres above sea level. That was a port 2,000 years ago. The city of Lydia, where gold coins were first made. I've been down the main street of Lydia. in a yacht. Lydia was about 4 metres beneath me off the south coast of Turkey. So we have the land level going up and down all the time. We have Holland, the Netherlands going down, Scandinavia going up. We've got Scotland going up and southeastern England going down. This is quite normal. So you can't talk about sea level unless you talk about the land level. And the land level is local. Some parts are sinking, other parts are rising, other parts are not changing. So in the peak of the last glaciation, there was thick ice over much of Europe, Canada, Russia. And that thick ice started to melt about 14,000 years ago, but started to melt very quickly about 12,000 years ago. And in between 12,000 years ago and 6,000 years ago, sea level has gone up 130 metres. Sea level was going up that much every year for 6,000 years. That's the sea level rise, not the millimetres that people worry about. And we had sudden warming driven by the orbit of the Earth and also helped along by the sun. Then we went into a sudden cold period for 1100 years called the Younger Dryas. This is when you humans invented agriculture. This is when you invented villages. This is when you invented animal husbandry. You started to keep sheep and goats and cattle. Then we suddenly came out of that into a warm period. Then we went back into another cold period for about 500 years. We know that because the people from the Anatolian highlands went down into the Black Sea basin, which then had no water in it. And then 6,000 years ago, we were at the peak of the current interglacial. 6,000 years ago, it was a few degrees warmer than now. 6,000 years ago, sea level was about 2 metres higher than now. And then we continued to have this warming and cooling. So, for example, in Greek and Roman times, it was warm. We know it was warm because the Romans planted olives right up the Rhine Valley as far as Bonn. The Romans planted grapevines in Yorkshire, in northern Yorkshire in England. You couldn't grow grapes there today. It was warm in Roman times. We know from the records of their salt harvests that it was warm. And we had 450 years of warming, where it was much warmer than now. And what did sea level do? Nothing. Sea level didn't change. And then we came into a very cold period of time called the Dark Ages. That started when three things happened, coincidentally. We had a tropical volcano of Krakatoa explode in 535 and put aerosols into the atmosphere. We had another tropical volcano in 536 in Rubal in Papua New Guinea, put aerosols into the atmosphere, and the sun got a bit quiet and we suddenly came into the Dark Ages. Crops failed. There was starvation. There was cannibalism. The weakened population got killed with the plague. Constantinople lost 60% of its people. And in cold times, we die. In warm times, we thrive. We really love warm times. And then we came back into a warm period of time, 900 AD, driven by the sun. And the first to feel it were the Vikings. And we know that because the Viking graves were deep. There was no permafrost. The Vikings grew barley. The Vikings grew wheat. The oceans were calmer and they were able to go across to Canada, to Newfoundland, and they grew grapes in a place called Vinland in Newfoundland. You couldn't do that today. It was much warmer in that period of medieval warming. And that medieval warming period went for 400 years. One cold period in the middle, but in the medieval warming, we knew that every year our crops were going to be good. We knew in the medieval warming that we would eat next year. And we had excess money because we were so successful. That money went into building the monasteries and cathedrals and universities, which you see in Europe. And the population grew enormously. And then the sun started to become a little bit inactive. And it took 23 years to go from the medieval warming into the Little Ice Age. And 23 years we went from wonderful times into times when crops failed, when there was famine, when there was starvation, when there was cannibalism. And in 1347 the plague came into Europe because the population was weak. And we had some extremely cold periods when the sun was really inactive, and the last very cold period was 330 years ago. That was called the Maunder minimum. We have been warming for 330 years. And since we've been measuring temperature with thermometers, we see warming and cooling. We were warming from 1850 to about 1890. Then we were cooling until 1910. Then we were warming until 1940. Then we were cooling until 1977. Then we were warming until 1997, and since then the satellite records tell us we are cooling, and the thermometer records say that there's been no temperature change. So what we see when we look in the history of time, cycles of climate, we see big accidental events like supernova eruptions and volcanoes and continents pulling apart. And what we see is enormous and rapid variability. So one of the reasons I wrote this book was that people are being told in the community, especially in schools, that trace amounts of a trace gas that we are adding to the atmosphere is driving climate change. And in the past, when we've had much more carbon dioxide in the atmosphere, we can see that climate change was driven by many other factors, often when there was coincidental factors. My concern in education is that our young people are being told something which is absolutely demonstrably incorrect. Carbon dioxide is plant food. Without carbon dioxide, we have no photosynthesis. So that's something that concerns me. And it's something that concerns me that the past is ignored. Anything we measure today is within variability. Anything we measure today is not surprising. There's nothing unusual about the world we are living in. And anything we measure today, you have to ask the questions. When was it measured? Who measured it? What was the method of measurement? What were the corrections applied? And what data was not looked at? And this has concerned me a lot, that a lot of data that we have about planet Earth has not been considered when we are setting up computer models. So we've had science divide into a group of scientists who use computer models, and they predict that we're going to die and fry, and other scientists like myself who are empiricists, who actually collect the data, and we see that we are living on a dynamic planet, that things are always changing. So I have a fundamental objection to the current popular paradigm that humans are changing climate, firstly on grounds of logic, secondly on grounds of looking at the past, and thirdly about the nature of science. Now what we've seen, certainly in many parts of the world, is that we have not had discussion about the science. This book is written, it's got an introduction of basically what I gave you then, and then it's got 101 questions which school children can ask their teacher just to find out if they're getting educated or if they're getting an ideology given to them. And there are some questions which are quite seditious. For example, Al Gore is telling us that sea level is going to rise 8 metres. Why does he buy a house next to the water? Explain that. We're being told that every year 3% of carbon dioxide put into the atmosphere comes from humans, and 97% is natural. Yet we're being told that that 3% changes climate and the 97% doesn't. We're being told that carbon dioxide is the main greenhouse gas. It isn't. It's water vapour. And it's very hard to tax water vapour. So I wrote this book because I think, from having spent 40 years in education, I've been seeing young people with less ability to think critically, less knowledge and less ability to analyse, and these young people are being given ideas, but they don't have the weapons that we gained in the Enlightenment for evaluating whether these ideas are valid or not. And the easiest way to find out if you are being fed propaganda or if you're being taught science is to ask questions. Some of these questions are for Friday afternoon. So if the teacher really objects to you asking questions and you get thrown outside, well, you've got a long weekend in front of you. Terrific. So this book is deliberately seditious. This book has been constructed because I've been concerned about the evolution of knowledge. And this book is written because all we hear about climate change is about models. We don't hear about what climate has done in the past. I have really good news for you, and that is the planet is healthy. We also must be very mindful that no one is arguing that we pollute the soil or the air or the water. You've only got to go to China to see what that does. Pollution kills you. It shortens your life. Those people here who are a little bit older would remember what parts of this country were like. I first came here in 1977, again in 1983, again in 1985. This country was polluted then. It is far less polluted now. Pollution kills you, but carbon dioxide is not a pollutant. It's plant food. But it's a wonderful thing to scare people about because you can't smell it and you can't see it. And we humans are hardwired through evolution to be fearful. We have to be fearful to survive. We need something to fear. The current fear is global warming. I don't know what it will be tomorrow. I think in the past the fear was a nuclear holocaust. So welcome to the world. You're a human, you're fragile, you have your fears, but the history of the planet shows us that we are living on a perfectly normal period of time on planet Earth, and maybe we have better things to worry about for the future of people on this planet than human-induced global warming. So I finish there and invite questions.
Just question to all of us. Can we compare the concentration of carbon dioxide here now and concentration of water vapor, amount of water vapor in the air here now, and carbon dioxide? Let's say it's about 400 ppm carbon dioxide. How much water vapor is here in terms of ppm?
You want to comment?
It's a question.
A question.
Not to you, but you know it. Okay, well, how to do it? It's about, if it is 100% humidity, it's 18 grams at 21 degrees. 18 grams of water vapor in 1 cubic meter, how much ppm is it? Because IPCC gives ppm volume, CO2 ppm volume, methane, but grams water vapor. It's 22,400 ppm. And if you have air 40 degrees, it could have even 45,000 ppm. So water is very important, and carbon dioxide is nothing. I just wanted to say that we really are exposed to that theory.
Well, let me just add to that. water vapour is wonderful, because if we have wet soil and we evaporate, we have the adiabatic heat of evaporation. And then when you have and we shift that water somewhere else and we precipitate it as rain. So we actually keep this planet in a stable temperature range because of water. We have a very slight increase in temperature due to carbon dioxide. And if we doubled the carbon dioxide content, we'd have about a 0.2 degrees Celsius temperature rise, because it's a log relationship. If we doubled it again, it would be less. And we know that. We know that because in the geological past, we had very high atmospheric carbon dioxide, yet we had ice ages. And we know we can live in higher carbon dioxide. Because this room is closed and not well air conditioned, we would have about 1,000 parts per million water vapour, 1,000 parts per million carbon dioxide in the air in this room. In a submarine, you have about 8% carbon dioxide. So we can live in a fairly big range of carbon dioxide. And we are driven by two very important things. Our climate on this planet is driven by the sun and its effect on water. Everything else is minor. That is the major driving force.
Thank you very much for your presentation. It was really interesting. I'm just wondering about the sun cycles, because it probably also has some influences on the climate changes.
The sun has cycles. We have a solar constant, which isn't constant, and we have cycles every 1,500 years, every 210 years, every 87 years, and every 22 years. And these solar cycles we can measure not only with light and heat, but with X-rays, with UV. We can measure it with sunspots, and we're in sunspot cycle 24, so we've been measuring this for 250 years. And we know that if we have very few sunspots, and instead of 11 years between the sunspot cycle, we have 12 or 13 years, we know we're facing cold times. That's exactly the period we're in now, and we've been like that for 5 years, where we've had a decrease in the number of sunspots and where the sunspot cycle has expanded beyond the 11.1 years. So the cycles of the sun are absolutely vital. And you heard it here first. That great ball of heat in the sky, called the sun, drives climate. And if it changes the amount of energy it releases, then climate will change. And if we set up low-level clouds from cosmic radiation, that will also affect climate. So there's some very complex work that's been done on cosmic radiation, the sun's magnetic field, and clouds. But the sun has cycles. Now, the cycles which we enjoy on the planet is every 143 million years, we are in the wrong address. And we get more cosmic radiation because we're in the wrong part of the galaxy. And every 143 million years, we look as if we have cooler times, sometimes an ice age. Then we have the orbital cycles of 100,000, 41,000 and 20,000 years. Then we have the solar cycles of 1,500, 210, 87 and 22 years. Then we've got the lunar tidal node cycle every 18.6 years. Then we've got the ocean decadal cycles about every 60 years. And then we've got accidental events. So you put a couple of these together and climate will change very, very quickly. Climate isn't just about a trace gas called carbon dioxide. It's far more complicated. That's the answer. I've forgotten your question.
So you mentioned already the dramatic changes in of the Earth or the globe in history. I think there are also the Milankovitch cycling which is responsible for that. So that means there are some changes of a vertical axis of our globe around the elliptic route around the sun. I think this would be a good way how to call physicists to explore and how to maybe develop another theory, because the number of years for one cycle which is leading to the glacial or interglacial period and so on is, let's say, 10 power to 4 years or even 10 power to 5 years. So that means 10,000 or 100,000 years. Is there anything which is being explored by some, let's say, NASA or the other organization in our, let's say, top of exploration?
I was referring to the Milankovitch cycles when I was talking about 100,000 years, 41,000 years and 20,000 years. We have known for a very long period of time that glaciation in Europe is driven by the Milankovitch cycles. We can see it from the chemical fingerprints in ice cores that have driven it, but there's another factor related to Milankovitch cycles. When we put ice on the poles of the Earth, it gets a bit fat in the middle. And that changes the spin of the Earth, which changes the ocean currents, which changes the distribution of heat. That never gets talked about. Occasionally, and looking at the age group here, occasionally we have to change the clocks. We have to change time by 1 second. And you would remember reading about this in the newspapers where time has changed. That's because we've changed the spin of the Earth, because we're changing the amount of ice on the poles and we're changing ocean currents as a result. The Milankovitch cycles at present is a major driver of climate. And we can go back millions of years and still see it was a major driver of climate. If we go back to the glaciation of 800 to 600 million years ago, we can see Milankovitch cycles in tidal sediments. We can also calculate that the length of the day has changed. We can also, because we are changing the spin of the Earth. We can also, and partly that's due to the moon moving away from the Earth about that much every year. We can also see that the Earth had a year of about 480 days. So it's been changing, but we can still see these Milankovitch cycles right back 600, 800 million years ago. And these wobbles that we get in the Earth's orbit obviously get us further or closer to the sun and obviously drive climate. And if we're in a very cold period of time, that's the Milankovitch cycles drive life and death. If we're in a warm period of time, it's just between warm and a little bit less warm. But as I say, the past is the key to the present, and if we don't look at the past cycles, we will not understand our present climate. And I will not make the mistake of making great predictions about the future, because if you do, you're wrong.
What do you think about effect of desertification or effect of large-scale deforestation on the regional climate or on the local climate, or how to say it?
I'll give an example, is the poster boy, Mount Kilimanjaro in Africa. And the ice has been retreating on Mount Kilimanjaro since about 1880. And that is directly related to land clearing, reducing the amount of precipitation. It's not that it's getting warmer, it's just that there's less snow falling because of the land clearing. And if you really want to do something to help the planet, plant more trees. The land clearing has had an effect on local climate. The land clearing has had an effect on the great dust storms that we saw in central USA in the 1930s and in my country. Land clearing has given us great dust storms. And the solution to that has been tried in many places and it works. plant trees. And if you really want to do something for the local environment, plant trees. Don't wave your hands about how we're going to fry and die due to climate change. Do something. So thank you for coming, folks.